Okay, so if we go back to our schematic example, we can modify this to think about the role that temperature is going to play on this. Because again, we talked about this in sort of an analogous way to think about the role of temperature in chemical equilibrium. You're also going to have a temperature dependency to where your equilibrium is going to be in terms of your distribution of heavy isotopes. So if you go back to this energy well example, if we think about hot settings, whether you're talking about hydrothermal spring with high waters, whether you're talking about really deep burial to high subsurface temperatures, if you're talking about Antarctic lakes or the sinking zones of your cold, dense water, you can imagine that this is going to kind of dictate where you're sitting in energy states. So the higher you go in temperature, the less you end up getting, what we're kind of showing schematically here, the less you end up getting a good energetic benefit, right? So you've kind of collapsed your zone. If you stuff a heavy isotope in here, maybe into the same sort of bond setting but at much higher temperatures, you don't get that much of an energetic benefit, right? So another way sort of conceptually to think about that is saying, high temperatures, you already have a lot of energy in the system, so it doesn't matter if you want to anthropomorphize it. It doesn't matter too much to a molecule which one goes in there. You're not going to save a lot. You're not going to see a lot of savings. Okay, and so this is your basis for what kind of started this whole game with oxygen isotope thermometry, and that's essentially what you're seeing a manifestation of when you look at these kinds of temperature versus fractionation plots. So if you go back to your schematic energy well, right? If you're down here at lower temperatures, it really matters, so you get more fractionation. If you're up here at higher temperatures, you have so much energy in the system, you're not getting much of a benefit, it doesn't matter much, you're not fractionating much. That's what you see in here, right? Greater fractionation at colder temperatures. Here's your magnitude of fractionation. That's the amount of sorting. They're really being picky down here. Here's you get up to higher temperatures. Sorry, opposite. There's not as much sorting. Okay, so this is, if you look into the basis for all of your stable isotope-based thermometers, whether you're looking in the high temperature realm, the low temperature realm, this is what's going on. Okay, questions on that? Okay, so we can superimpose clumped isotopes into this framework and make a prediction. So here we have the same things we looked at before. Here we're going to have our vibrational frequencies are lower when we add in a heavy isotope into a molecule. Now, if we add in, oh, I didn't animate these, I'm sorry. If you add these in, you can imagine that when you have two heavy isotopes kind of bonded together, the vibrational frequencies of that sort of bonded pair are even lower. And so essentially what you get is an even greater energetic benefit. And we've already talked about sort of our energetic motivations. Our goal is to lower our 0-point energy as much as possible. And so this predicts essentially that if you looked at the equilibrium exchange reaction for these isotopes, here you have a bunch of carbonate ions. At colder temperatures, this whole reaction is going to be pushed to the right-hand side because there's such an energetic benefit from getting two heavy isotopes substituted in that when you deal with colder temperatures, it's much more preferable to clump all of your heavy isotopes and leave some of your molecules, say, unclumped, than it is to kind of have your isotopes more randomly distributed. Okay, so same basic premise, this same idea. You're getting an energetic benefit. You're getting more of an energetic benefit when you stuff two heavy isotopes into a molecule. And so you create a temperature dependence to this reordering reaction. And at this point, I usually like to point out, so that's all the same physics you're kind of used to. And at this point, I like to point out a couple key differences. So in this original O18 thermometry equation, what you can see is you're looking at the exchange moving around, say, an O18 that's in your water and getting it bound within the carbonate. And we call this a heterogeneous isotope equilibrium, right? And this is because you're dealing with this is not strictly chemically correct, but from looking at where the isotopes are going, you're looking at exchange between two different chemical species, right? You've got water involved in this equation. You've got calcium carbonate involved in this equation. Here, what's sort of profoundly different about our clumped isotope thermometry is we're just interested in the reordering of isotopes among a single species. So this is our homogeneous equilibrium, right? Our single species in this particular version of the equation is just carbonate ions. So the only equilibrium you're interested in is finding that balance point, depending on temperature, of how your heavy isotopes are distributed among all of your available carbonate ions in whatever setting you're looking at. So that's one key twist to this thermometer that helps make it really powerful. And the other thing to know about is our reference point. So we've also talked about, you've talked about delta notation, and here we put our tool, we call this CAP47, put it into a similar delta framework. But you'll notice there's something different here, right? This says, what should that say if you're sort of looking at delta notation for delta 13C or delta 18O? What would be in that position? Standard. Yeah, and that might be PDB, that might be SMO, that might be whatever else is your reference framework for your particular isotope here. And you would call that kind of, I would call that a static reference point, right? Somebody took that PD belemnite shell, they measured it over and over and over again until they had some really good average number, and then they said, okay, we're calling that 0. And that became your reference point. It's always the same place every time you kind of use that reference point. Here, we have what's called a dynamic reference point, and it's basically the stochastic distribution of heavy isotopes available in a setting. So we've already talked about this sort of temperature dependence of this system is entirely based on sort of cold temperatures promoting more clumping. So you can imagine at hot temperatures, you're going to move, really high temperatures, you're going to move to a more random or stochastic distribution. So that stochastic distribution is what sets our framework. You can also imagine, I call it a dynamic reference point because it's going to be different probably for every fluid you're precipitating a mineral out of. Right? You could have two lakes next door to each other, and a plane flies by and drops a bomb of C13 and O18 into one lake, but they're at the same temperature. Which lake is likely, just on, if you were a betting person, which lake is just going to have more of these clumped mass 47 molecules in it? Yeah, you have more heavy isotopes, so even if you distribute them randomly, you'd expect, just based on odds, that you'd end up with a few more of these clumped bonds just completely randomly in terms of having a random distribution because you have more heavy isotopes available to make those clumped bonds. And so this is why we want this sort of dynamic reference point. We want to be able to account for the fact that you might have sort of different overall absolute abundances of heavy isotopes at your disposal to make your clumps from. Yes?
Sorry, does that R stochastic mean the random distribution of heavy isotopes expected or clumped isotopes?
It's the random distribution of, it's the abundance of clumped isotopes in your setting based on the prediction you'd make of the overall pool of available heavy isotopes. So that's a confusing way to say it, and I'll come back to what that means. So it's a calculated parameter basically using statistics to say, okay, if we have X number of C13s and X number of O18s, how many of these clumped bonds would we expect to get? And then that's essentially set reference to your 0 point. And I will restate that again on another slide. Okay, so these two key twists on our sort of familiar equilibrium exchange setting make this a really potentially powerful tool because one, your temperature ends up being independent from the oxygen isotopic composition, or overall your C13 or O18 composition of the fluid your mineral forms from. So that's a huge improvement in terms of kind of where we left off with O18 thermometry, particularly if you are like me and work in a terrestrial realm where the O18 of water can change a lot. And the other benefit is, as I said at the beginning, we measure this mass. If we have a mass spectrometer as a right number of detectors, we measure this mass at the same time we're measuring masses 44 through 46. So from one analysis on the mass spec, we get your carbon isotope composition of the carbonate, you get the O18 value of your carbonate, and you get this measure of temperature of mineral formation. So you can actually combine that temperature with the O18 of your carbonate and make a constrained estimate of the O18 of the water that mineral forms from that is specific to that sample. So for those of you who do play games in the geologic realm, this is really powerful. This is two separate pieces of climatic, environmental information in the geologic record that we potentially now have access to that can tell us a lot of different things about an environment. Okay, so I said I would come back to sort of this concept of what does this reference point really mean? And I don't want you to worry too much about the math here, but essentially this is a version. So if you were going to go look in all the calculation sheets that actually come out of the mass spec, like the kinds of data you're getting for all of your other isotope systems, and look at how they calculate this CAP47 value, you would end up seeing all of these different parameters. And you have these 47 ratio, 46 ratio, and 45 ratio star values, which are essentially your expected stochastic value. So it's calculated, and these are the equations they use to actually calculate that. And you can see it factors in, essentially, a lot of knowledge of your C13 ratios and your O18 ratios. So again, we're making all these measurements at once. So in terms of your heavy isotopes, the C13, your mass 44 and your mass 45, or in other words, your C13 and O18 abundance, so much greater than your clumped abundance that we can essentially use your C13 and O18 values as a measure of the availability of heavy C13 and O18 molecules within your system. So if you have really negative delta 13C values, really negative O18 values, you're going to end up in different sort of clump space with a different reference point than if you have really heavy delta 13C values and really heavy delta 18O values. Does that make sense? Okay. Are there any questions about, so that was the sort of mechanical explanation I wanted to go through in terms of explaining this thermometer and how it works and why you get this temperature-dependent clumping. So at this point, I'll take any other questions that still seem confusing. John?
Sorry, going back to the increase in temperature. As you said, as you increase the temperature, you get less of an energetic benefit.
Mm-hmm.
Do you get to a point where that goes completely away?
I mean, in essence, at very, very high temperatures. So if you look at the people who are probably the most rigorous in terms of their analytical precision early on in doing this were all these folks, say, in the metamorphic petrology end of the world who wanted to use this as a geothermometry. So they wanted to know about temperature of metamorphic reactions and other things going on deeper within the Earth. And those signals are so small that very early on they were really hard to measure. So these were some of the best analysts out there because every single 100th to a 10th of a per mil counted on the high temperature realm. But yes, there is a point at which there are two different aspects to it. There's a point at which it should exist, but you may not be able to measure it. And then there's also a point at which, right, you reach dissociation, right? That's kind of in those energy diagrams. That's the curved right-hand side. When you hit that point, your bond's going to break, and then everything is allowed to start exchanging. So.
When we talk about clumping, are we talking about two heavy isotopes being bonded to each other on the same molecule, or just bonded on the same molecule? Does that make sense?
So that's a good question. Typically, we talk about it mostly as when these things are bonded to each other. When you start exploring the world of all of these other molecules, you can imagine that you might end up with, and you may even end up with these in one of your groups. I don't know if I didn't use up all of my CO2 molecules here, but you can imagine, carbon, CO2, the carbon sitting in the middle, so you might end up with oxygen 18s on either side, and there might be a thermodynamic control for that, but predicting that and kind of predicting the behavior is going to be slightly different than when they're kind of bonded to each other, and what energetic benefit you get out of that configuration is going to be different. I'll talk about this a little bit more at the end. I have a couple of slides about other applications. But there are people who are really interested not just in the clumping, but in terms of thinking about all these multiply substituted isotopologues, which is a mouthful, which is why John Eiler started saying clumps, where they are interested in specifically where those heavy isotopes go. And you can imagine, so CO2, as Naomi mentioned yesterday, is a symmetric molecule. So you have the carbon in the middle and oxygen on either side. If you look at N2O, you're looking at NNO. So where you put that heavy isotope matters a lot in terms of thinking about its vibrational energy and how it might behave. And so if you dig into some of those literature and you look at how N2O might behave in some of these things, its sort of pathway through equilibrium and in kinetic reactions looks a good deal different than CO2, simply because the structure of the molecule is different. So typically we're talking about the clumped bonds, but there's a lot of other information when you are talking about multiple substitutions, even if they aren't bonded to each other. Yep. Yep.
Can you explain again what you mean by when you know the delta 18 of carbonate, then you can best estimate the 16 water?
Yeah, so if you go back to, so our traditional O18 thermometer is based on this exchange of, say, O18 with the fluid that the carbonate mineral is forming from. So if you look at this example, we always measured, to do your C13 and O18 in carbonate, you would measure mass 44, 45, and 46 of CO2 that was evolved from that carbonate, right? So you've already gotten your C13 and your O18 values. In this case, we're just adding one more. In the case of clumped isotope thermometry, we're adding one more mass. So we have another detector. We're measuring it at the exact same time. And so you get simultaneously your carbon isotope value of that carbonate. You get the O18 value of that carbonate. And you get the temperature at that carbonate. And so you're basically taking this original thermometry equation, right, that people developed to get temperature out of and had to make an assumption of the O18 of water. And we're going backwards and saying, well, now we have this way of getting this parameter. We have a way of measuring temperature, comes from the exact same sample, but it's independent from this reaction. So we can take that temperature, plug it into this equation, and back out the O18 of water.